And if you look at the periodic table, you'll see that the elements are kind of arranged by atomic mass, but not really. And that's because we have something. Like at the top of the periodic table, yes, that kind of still holds true, but there's something else we really look at now. So now, you know, and this doesn't have a pencil on it, but you still need to understand it and write it. So, but now what happened is like current scientists are like, okay, that was cool what you came up with, but what about isotopes? If you have an isotope, it's going to have a greater mass, but you still place it in the same spot on the periodic table. So instead, now we arrange elements based off of the atomic mass number as opposed to the atomic mass, sorry, the atomic number as opposed to the atomic mass. And so the current theory about the periodic table is that when you arrange elements based off of their atomic number, there will be a pattern that will enable you to be able to predict their physical and chemical properties. So based off of the location of an element on the periodic table, you can figure out so much stuff about it. You'll know, you can have an idea about its melting point, its boiling point, whether or not it can conduct electricity, what state of matter will it normally be in. So all of that you can learn from an element just based off of where it resides on the periodic table. And that comes from arranging them by their atomic numbers. So back in the day, we did it by mass. Now we do it by atomic number. So when you're looking at the periodic table, we have groups, periods, and families. So the groups, the columns of the periodic table are referred to as groups. So each column is called a group. You will also, I didn't write it on here, but you will also hear groups referred to as families. So all the columns in the periodic table are called either groups or families. And then the rows on the periodic table are known as periods. And the reason why the groups are called families is because elements that are in the same column have a lot of the same properties. So helium, lithium, nitrogen, potassium, rubidium. Sorry, that's not helium. Lithium, sodium, potassium, rubidium, cesium, and francium, they all have very similar characteristics. So there's something about them that's similar. Lithium is more similar to sodium than it is to beryllium. And you can tell that just based off of the fact that lithium and sodium are in the same column. All right. So there's different categories of elements. And the first category we're going to talk about, and I kind of mentioned it earlier in class, are the noble gases. So the noble gases, they are in that last column on the right-hand side of the periodic table. And that column is called group 8. Sometimes you will see it called group 8A, like 8 with the letter A. The thing that is so unique about these particular elements is that they are not reactive at all. And they're not reactive because they're super, super stable. And they're super stable because they have 8 valence shell electrons. So remember yesterday I talked about, I think it was yesterday, how I mentioned that the valence shell is the outermost shell of an atom. And so noble gases have 8 electrons on that. So remember when we were doing the Bohr model, you had 2 electrons on the first shell and every shell after that could hold up to 8. So 8 means like the shell is full. And if an atom has a full shell, it is stable, it is happy. If it has 7 or 2 or 4, it's going to try to bond with other elements. It's going to try to steal electrons from something else or say, hey, can we share? So it's going to do a lot. It's going to be very reactive because the whole thing is atoms are just trying to get 8 electrons on that outer shell. Since noble gases already have 8 electrons on their outer shell, they're not going to react with anyone because they don't want to give away electrons and they don't want to take electrons away from anybody. So they don't react with anyone and they don't really bond unless you force them. You can force noble gases to bond to each other or something else, but for the most part, they're not going to bond. All right. And so all the noble gases will have 8 valence electrons except for helium. And that is because helium, if you look on the periodic table, helium is in that noble gas family. But remember, when you're drawing Bohr models, it goes 2, 8, 8, 8, 8, 8, 8. So since helium only has that first shell, the fact that it only has 2 valence electrons, it makes it full. It's stable because that first shell is full. So then the next category are group A elements. I'll explain group A when I'm going to show you a periodic table and kind of explain a little bit better in a second. But all the elements in group A, and basically everything other than noble gases, they're going to have partially filled sublevels. So that just means that they don't have a completely full valence shell. And the group number will tell you how many electrons are present. So if I refer to group 3A, then you automatically know that those elements have 3 valence electrons. If we're talking about group 4A, you know they have 4 valence electrons, 1A, 2A, whatever. It's going to tell you how many valence electrons they have. Sometimes, so I'll just go through this. All right, so we have group 1A, and these are known as your alkali earth metals. So this is the very first column in the periodic table. These are group 1A. So everything in this column right here is considered an alkali earth metal, with the exception of helium, not helium, with the exception of hydrogen. Hydrogen is funky and also it's not a metal, so it's not an earth metal. But lithium, nitrogen, potassium, rubidium, cesium, and francium, all of those are alkali earth metals. And they are going to be very, very, very reactive. Those are, if you get them in a pure form and you mix them, you like just drop them in water, they will like explode because that's how reactive they are. And once again, it's group 1A, so you know they're going to have 1 valence electron. Sometimes you will see it just referred to as group 1. So the number 1 tells you A, what column you're dealing with and how many valence electrons you have. Then we go to group 2A. So it's the second column of the periodic table. And you know it has 2 valence shell electrons, and these are called your alkaline earth metals. So they're also reactive, but they're not as reactive as your group 1. So group 1 are the most reactive, and then you have group 2. And then you have group 7. So group 7, or 7A, these are known as your halogens, and you need to know that term. These are known as your halogens, and they are the column right before your noble gases. So if you look on your periodic table, the column right before the noble gases, that's group 7 or group 7A, and those are called your halogens. And they are super, 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 super reactive too. So you may be saying, wait a minute, Dr. Hyde, you said that the alkali earth metals are the most reactive. Well, what are the halogens? So here's the thing though. The alkali earth metals are the most reactive metals. Your halogens are very reactive, but they're not metals. They're actually mostly gases. And then right here, this word diatomic, these are typically found in diatomic form. And what that means, di means 2. So that means that these elements don't really like to chill by themselves. So you'll rarely see fluorine, you rarely just see a single molecule of fluorine. Usually you'll see 2 fluorines bound together. Don't worry about that yet. We'll talk more about that in a later unit, but that's what that means. And let me come out of this so I can pull up a periodic table and kind of show you what is meant by group A. Okay, so group A, because we're going to talk about group B in a second. I kind of look at the periodic table as like a house. I don't know, to me it looks like a castle or something. And so group A are our pillars. So we have these 2, well basically our S block and our P block. that is what is referred to as group A. This depressed section right here, the D block and the F block, those are not part of group A. So when we're saying group 4A, you are not counting these rows right here. You are only counting the rows that are part of group A. So group 4A would be group 1, 2, 3, 4. So this would be, this column right here would be part of group 4. Sometimes, like I said, you'll hear it called this can be either called group 4A or group 4. Sometimes you won't even see the A. No one really refers to these down here by their row. If you hear, I'm sorry, by their column. If you hear someone talking about a column or a group, they're typically referring to just these and these. So this is group 1, group 2, group 3, 4, 5, 6, 7, and 8. All right. Okay. So now we move on. And remember, whatever group you're in, whatever group number you're in, that tells you how many valence electrons you have. So if you're in group 5 or group 5A, you're going to have 5 valence electrons. Go away. Okay. So now we're into group B. So group B are your transition metals. Only thing you need to know where to find them on the periodic table. So those are all of your D block. So on the periodic table, that whole little section of where it's like sunken down, those are your transition metals. That's all you need to know. Nothing really characteristic about them. There's not like a true pattern that we're going to learn about. All right, so now we're moving on to our inner transition metals. So our inner transition metals are just those 2 rows that are at the bottom of your periodic table. And the majority of the elements down here are man-made. The thing that I want you to keep in mind is that all the inner transition metals are part of the F sublevels. So your 4F and your 5F. And there's 2 components to your inner transition metals. You have the lanthanide series, so that's just the first row. And then you have the actinide series, which is the second row. And you can figure out, if you get confused on like actinide and lanthanide, if you look on your periodic table, those these 2 boxes are actually in your periodic table, but it just kind of shows you where those rows are actually inserted. And you can also look at the numbering too, because you see the number on our periodic table. It goes from 57 to 72. Well, you know something must have happened. So that's when you look down here to pick it up. Good. All right. So those are the different, what are those? Those are the different categories. So now let's go to the different types of elements. So now we have metals. So you'll need to pull out your periodic table. We're going to write on it, color on it, or whatever you want to do on it, highlight it. I don't care. So you just get a periodic table that you can do something with. All right. So metals, you probably learned this in 1st grade, if not preschool. Well, no, I don't know. So metals, they're going to be, they have a high conductivity, so they can conduct heat and electricity very, very well. You guys know that. I don't really have to tell you guys that. Metals are solid at room temperature. Typically, I should say typically, there are some exceptions. So metals are going to typically be solid at room temperature. They're going to be very lustrous and shiny. So that just means they are bright. And malleable, that means that you can mold them and bend them and stuff like that. Like, even if it takes a little bit of work, but like you may have to take a hammer or something like that, but you can put them into thin sheets. And the key with that, the key to that is you can mold metal and it won't break. You can bend it and it won't break. It's very durable. And then it's also ductile. So on our periodic table, the metals, everything that is blue here, those are the metals on the periodic table. And PO, I think it's polonium. Yeah, polonium, it's intentionally tinged green. So you're not going to include that with your metals. You're going to stop your metals right here at bismuth. So you can highlight, you can outline, you can color it in. Just do something on your periodic table so that you know that these are your metals, including these two rows at the bottom here. These are your metals. All right, if you don't got it, it's okay because this slide will keep popping back up. Sorry, I got distracted. I forgot what I was doing. And I was like, oh yeah, teaching. So the next topic, the next type, category, whatever, are nonmetals. So these are just the opposite of metals. So these are going to be elements or atoms that are going to be poor conductors of electricity and heat. They are typically gases, especially at room temperature. Doesn't mean that they will not be solids. Everything can become a solid. So when these nonmetals become solids, they're going to be very brittle. And a good example is if you think about carbon. So carbon, room temperature, is a gas. But then when it comes into a solid form under enough pressure, it's coal, and coal is very brittle, and it's also dull. So then when we're looking at our periodic table, well, where are the nonmetals? So the nonmetals are the yellow. And when you're doing nonmetals, don't forget hydrogen. So even though hydrogen's over here on the left-hand side with all the metals, it is still a non-metal. So you want to make sure you include it. And then actinide, whatever this is, it's intentionally tinged green. So you want to leave it out of the nonmetals. So your nonmetals right here would be iodine, xenon, and radon. Oops, okay, good. So now we have to move on to our third and final type, which are metalloids. So basically metalloids, they don't really have any true properties. They're just, if you have an element that's a little bit of column A, a little bit of column B, there should only be 2 bullets here. This is all 1 bullet. It just came out into 2. So it's just to say form a step ladder type pattern. But yeah, so your metalloids are just elements that have a little bit of both. They could be solids that don't conduct electricity. Yeah, or they could be shiny solids. I don't know. But you get what I'm saying? Like they have a little bit of each. So they're not really metals and they're not really non-metals. So when you're looking on your periodic table, sometimes you'll see it referred to as the stair step because it is basically a stair step down the side of your periodic table. But these are your metalloids right here, the green ones. And so polonium and astatine, whatever it's called, they are considered metalloids. But polonium, for example, it is a metalloid, but it's more metal than non-metal. So that's why it's kind of blue with a green. And then this one is more non-metal than metalloid. So that's why it has a more of a yellow color to it. But they're still considered metalloids. And the cool thing is I guess it makes perfect sense because if you think about it, like you have all these metals on the periodic table and on the left-hand side, and then your non-metals on the right-hand side. And then metalloids are just kind of like that gradient that introduces the next type of elements. And I believe on the reference table, you would get like the state gives you, it's not labeled metal, metalloid, and non-metal, but the stair step is clearly labeled. So therefore you would know that if it's to the right of the stair step, it's going to be a non-metal. And if it's to the left of the stair step, it is a metal. And then you're good to go. But when in doubt, assume it's a metal because as you can see, majority of the periodic table are metals. Okay, so that is the end of notes today. For homework, when you, let me stop this.